Okay, welcome to the lecture and introduction to large deviations. And today we will discuss contraction principle and Friedlin-Wenzel theory. Namely, we will prove the large deviation principle for some class of stochastic differential equations. You can find the material of this lecture in lecture notes on the web page, and it is the section number 8. I will write that here, 8. Contraction principle. And Friedlin Wenzel theory. And we will start from the contraction principle. And to formulate the contraction principle, maybe it makes sense to recall you the definition of large deviations, since we will work today with it. And then the contraction principle allows to transfer the given large deviation principle to another large deviation principle under some under continuous maps. Therefore, recall that a family of random variables that we usually denote by psi epsilon in a metric space E satisfies the large deviation principle in that space with rate function I, that is the function from that space, from that metric space to 0 plus infinity also is allowed. If we have two properties, we had two different formulations of large deviation principle. Today, for me, it will be convenient via closed and open sets. One for every f closed in E. One has the upper bound, the probability psi epsilon belongs to f can be bounded from above by minus infimum rate function over the set, and infimum is taken over the set f, and the second for every open set G open in E. One has that the limit epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to f is larger or equal than minus infimum I, and here G. Now let's assume that, or let's consider the following picture. Assume that we have the space E. It is space E. And here we have the family of random variables psi epsilon. And then consider a function f from this space to another space that we, for instance, denote by S, and also it is a metric space. And now we define here the random variables that is f of psi epsilon. If you like, we can for a moment denote that by eta epsilon. Then the contraction principle will tell us that if this family satisfies the large deviation principle, then this family also will satisfy the large deviation principle. Moreover, we know how to define the rate function for this this family of random variables. Maybe also it makes sense here to also sketch the rate function. Actually, the rate function is a function that takes values from 0 to plus infinity. And here we have the rate function I. And let's denote the rate function here by J. Oh, therefore, the following statement holds. Um, Maybe it's better to make this picture a little bit smaller. Put it here. Um, Theorem 8.1. It's contraction principle. Contraction principle. Let's consider a continuous function as in as on the picture from E to S, where E, comma S are metric spaces. Yes. And let psi epsilon be a family of random variables in E that satisfies the large deviation principle in E with rate function I. Then the images f psi epsilon satisfies the large deviation principle in S with rate function j that is defined as follows. Everything what you need to do, you just take the infimum of the function I of x over all pre-images, roughly speaking, over all x that are mapped to y. That is I of s such that f of x is equal to y. In other words, you can also write that as the infimum over the set f minus 1 of y I. Let me maybe sketch that situation on the picture. If you have here y, then you consider the pre-image, it is all x that are mapped to this point y. And then the rate function j here is equal to, I will write also here, j of y is equal to infimum of I of x of this function, which is here of that rate function, where you compute this infimum over that set. Here is that infimum. So this set is f minus 1 of y, and then you take infimum over f minus 1 of y. Okay, everything very simple. I mean, very concrete form of the rate function. And you see that here we don't need any further assumptions on the function f, only the continuity. Also, I would like to add here, I don't have place to write that on this page. Let me write it here. Moreover, G is a good rate function. It means that level sets are compact for every alpha positive if or equal to 0, uh, or whenever the rate function or the function f is good. Here is compact. Okay, that is a statement, and let's prove. You will see that indeed the proof is like a few lines computations. But from another side, this statement, as I remarked, it is really very powerful, and you can use that in many different situations. And also, we will do that today when we will discuss the large deviation principle for stochastic differential equations, because we can build a continuous function that will map a Brownian motion to the solutions of stochastic differential equations. These equations will have a special type that where that function can be easily constructed. And also next time we will discuss the Sanov theorem, the large deviation principle for empirical distributions, and also in some situation it can be that theorem can be easily obtained from the contraction principle. Now we will prove. And we start from the upper bound. We take f, but now f is a subset of S because we want to prove the large deviation principle in S. And we take that f closed set and note that the preimage of f that is defined as all x such that f of x belongs to to f, I'm sorry, is closed in E. The closeness follows from the continuity, and that is exactly the critical point where you need the continuity that the preimage of closed set is closed, and later also preimage of open set also is open, and that will be used in the following computation. Then let's write lim epsilon goes to 0, epsilon that is the lim sup logarithm the probability that f of psi epsilon belongs to f. And this is the same as limit epsilon logarithm probability, but here you just write psi epsilon belongs to the preimage. But now recall that that set is closed. And when we go a few pages back, you see that large deviation principle, that inequality is satisfied for closed sets, in particular for set of that form. It is less or equal than minus infimum over all x that belongs to f minus 1 of f of I of x. And here maybe also we need the picture just to better understand what is going on. You have the set f here, and that is a subset of the space S, and then you have the preimage of that set. Maybe it's let's use another color. It is F, and then you have E. Then you consider the map F, and then the preimage. It is, for instance, that set. It is f minus 1 of f. And then what you do here, you just take the infimum of the function over this set. But this infimum, which is here, we also can compute differently. We can we can fix or go through all points of f, and then consider the preimages of that point. So for instance, that point, it is mapped to that point under the f, the function f. And when you go through all points, you will cover that completely this set. So therefore, this infimum, it can be written as minus infimum, and first you go y belongs to f, and then infimum of of let's write all x such that f of x is equal to y of I of x. But the function which is here, it is exactly the function j. If you go here, you see that we compute the infimum of I of x over all x that is equal to y. Then it is it is minus infimum y belongs to f j of y. By the way, the same bound will work, or the same lower, or similarly, the lower bound also can be obtained. The lower bound, uh, let me specify for G open, can be proved similar. Can be proved similarly. Okay, and it is exactly the proof of contraction principle. It remains only to prove this additional part of the statement that if the function I, oops, I apologize, here should be, of course, here should be I. If the function I is good function, good rate function, then the function J also is good function, good rate function. And to see that, so let I be a good rate function. Then we will show that the level set for j that is less or equal than alpha is equal to the image of level set for I. But you remember that this is compact. And you know that image of compact set under continuous map is compact. Therefore, this compact since f is continuous. If you do not know that property, you can, for instance, you can prove that easily using only the definition of compact sets. For instance, you can go via the open covers of sets, and then you can, and using the fact that the pre-image of the f of open set is also open, you can simply see that compactness is preserved under continuous maps. We want to show that for every alpha larger or equal than 0. And to see this, let's fix alpha. And first of all, okay, let's step by step. Fix alpha that is larger or equal than, and let x belongs to the level set for I. That means that I of x is less or equal than alpha. Then what you can conclude? You can conclude that j of f of x is equal to infimum over all, for instance, now u, such that f of u is equal to f of x. So we cannot use here x anymore, like we did that in the definition of j, because x was reserved later. So we write u, but you see that now that this at that point it is infimum of that over all u, such that f of u is equal to this point. So that point and that points are the same. But now you also see that if you take u is equal to x, if here is x, then simply the equality is satisfied. Therefore, you take that infimum over the set that includes, including that contains the point x. Therefore, this infimum, it can be only smaller or equal than I of x. But you remember that it is less or equal than alpha. So this means This means that that f of x belongs to the level set alpha, right? It belongs because when you compute f of this point, what we did here, it will be less or equal than alpha. You see that from here. Then in particular, we started from a point x, and we show that f of x belongs to J. In particular, it means that f of every point is a subset of J less or equal than alpha. Now we want to prove the opposite inequality. Um, First of all, let's say that since that now uh, let y of so it is equal to let's recall that it is infimum over all so I of x such that f of x so maybe it's better to also use u here. U is equal to y, and this y it's from the level set. It's less or equal than alpha. This y is from level set. Now we want to show that y will belong to the image of that level set. So it will implies the inequality in opposite direction. But since I is good, that means that all level sets are compact. One can show that infimum here is attended at some point x. So since it's good, then there exists x from E such that we have that y is equal to f of x, and this actually x, it is so that it is that u for which you have that I of x is exactly this infimum. Maybe it makes sense to write that y of is equal to I of x. That of course is less or equal than alpha. Thus we have that y belongs to the image. And this implies exactly that j less or equal than alpha is a subset of f of I less or equal than alpha. That finishes the proof. Okay, now we know that if I is the good rate function, that j is also good rate function. Good. Now, for instance, maybe a few trivial examples. Just for instance, we know the large deviation principle for normal distributed random variables. Let's assume that xi has a normal distribution with parameter 0, 1. Then you have that xi epsilon, that's or square root epsilon xi, satisfies the large deviation principle in R with the good rate function that is I of x, it is equal to x squared divided by 2. But now consider, I do not know, maybe let's take now consider the family 1 plus square root epsilon xi. Then it satisfies the large deviation principle in R with, maybe here let's put A for instance, in R with the function j of y that is equal to, and here we want to compute, but let's first of all say that a plus square root epsilon xi, it is the function f of square root epsilon xi, where f, it is just shift, right? F of x, it is a plus x. So therefore, this j, it is infimum over all, so it is I of x, so that f of x is equal to y. Or it is the same as you will write that it is infimum I of x such that, and then you have a plus x is equal to y. So it is bijective map. So therefore there is only one x for which you have that equality, and this immediately gives you that this rate function, it is a rate function of x, but for which x it is y minus a. That is y minus a square divided by 2. And you see how simply, just considering, for instance, that family of random variables, you see that the rate function is given by that formula, and you also know that it satisfies the large deviation principle. Okay, now we want to consider a more complicated example that is solution to stochastic differential equation. That is the next section. It is Freidlin-Wenzel theory. Wenzel theory. But before we will continue, let's make like 1 minute break. I will come back in a few minutes. Okay, I'm sorry for the interruption. And now Freidlin-Wenzel theory, and in this section we will work with the stochastic differential equations of the following form. Consider a family Z epsilon of solutions to the following stochastic differential equations. Of that is d z epsilon is equal to of t is equal to a z epsilon of t dt plus square root epsilon dwt, and with initial conditions that epsilon of 0 is equal to 0, similarly as for Brownian motion. When a from R to R is a bounded Lipschitz continuous function. it's clear what boundness mean, but what is Lipschitz continuity? Let's recall that f of x minus of x1 minus f of x2 is less or equal than L, some constant independent of x of x1 minus x2 for every x1, x2 from R. And W is a standard Brownian motion. Is a standard Brownian motion. If you never work with stochastic differential equations before, it is not a problem. Everything what you need to know about that equation, that it has a unique solution. In other words, there exists a continuous process. This continuous process is unique, almost surely, which satisfies the following equality. Of, let's write that this means, or we know that there exists a unique continuous process z such that z epsilon of t is equal to integral from 0 to t a z epsilon of s ds plus square root epsilon w of t, or t from 0 to t. It's not complicated to prove the existence of such a process using the fixed point argument, but we will not do that here. We will accept that as a fact, and then we will work with that process. And our goal now will be to show that this z can be defined as a continuous function of Brownian motion, of this Brownian motion. And since we know the large deviation principle for Brownian motion, then we will obtain almost for free the large deviation principle for that family, that epsilon, using the contraction principle. And to do that, first of all, we will formulate result, and then in the proof, we will build that continuous map, and we will imply the contraction principle. It is a theorem. 87, Freiling, Vance theorem. For any, or for maybe every, bounded Lipschitz continuous function A, from R to R, the solutions or the family of solutions z epsilon to the ACD is, let's repeat that. Satisfies the large deviation principle in the space C0, 0t, the space of continuous functions, and that function at 0 is equal to 0, with good rate function I of L is equal to 1 over 2 integral from 0 to t f dot of t minus a f of t. This dot, you remember that we work with absolutely continuous functions and that it is like a kind of derivative of that function. dt if f belongs to h0 to 0t and plus infinity otherwise. Okay, now proof via the contraction principle. Let's first of all we remark that the theory of ordinary differential equations give us that we remark that the integral equation z of t that is equal to from 0 to t a z of s ds plus g t has a unique solution for uh, for each continuous function g from c0 0 t. Since the function is bounded and is and Lipschitz continuous, maybe here it makes sense to tell a few words about the idea how that solution can be constructed. That idea. You take you approximate you build that the solution using approximation, and then you take z0 is equal to 0, for instance, and then you define zn plus 1 of t via zn of s ds plus g of t. And then it's not complicated to see that that family zn is a Cauchy sequence. In C0 0t. That gives the convergence, since the space C0 is complete metric space or normed space, and then that limit points is easy to see satisfy the equation, because when you pass to the limit here and you pass to the limit here, you will see the limiting process here and there that gives you exactly this process. I think that we don't need to discuss more. And now you see that you have a possibility for every function, continuous function g, construct a solution z. And this function that continuous function that I want to construct will exactly send each function g to the solution of the equation. Let's write that. No, that's they exist. Is a function. We do not know at the moment whether it is continuous or no. Phi from C0 0t to C0 0t such that we have that z is equal to phi of g. And now we want to show that this function is continuous. If the function is continuous, then note that z epsilon, it is phi of square root epsilon w. Therefore, if that function phi is continuous, then using the contraction principle, which we proved last time for the Brownian motion, we will get the large deviation principle for the solutions to this equation. Here also again typo, it should be plus, of course. To show the continuity, we will even show more. We will show the Lipschitz continuity of the function capital Phi. Let um, or take 2 points or 2 functions from the space of continuous functions starting from 0 and set z1 it is equal to phi of g1 and z2 is phi of g2. And let's estimate z1 of t minus z2 of t. Since z1 and z2 satisfy the differential equation, we have that so absolute value integral from 0 to t a of z1 of s minus a of z2 of s ds, and then plus g1 of t minus g2 of t minus g2 of t, and absolute value. Then using the triangle inequality and the Jensen inequality, triangle inequality, you can put absolute value here and there, and then Jensen inequality, you can just move the absolute value inside the integral. You have a z1 of s minus a z2 of s ds plus g1 of t minus g2 of t. Um, by the way, if you work already with stochastic differential equation, that we now we realize the idea which is standard in the theory of stochastic differential equations, that we want to estimate that absolute value via the integral of the same absolute value plus something, and then we want to use the granular inequality. It is exactly what we are doing here. Now, first of all, we use the Lipschitz continuity of A. Then we will have some constant L. You have z1 of s minus z2 of s ds plus. And here you can replace that absolute value by the supremum. You can write here, you can estimate by the supremum t from 0 to t. That is the norm in the space of continuous functions. The supremum norm. And you see that you have that your function that is not negative is estimated via the integral of the function plus some constant. And then using the Grunwald inequality by Walls inequality, we get that that function can be estimated by that constant, that is g1 minus g2 c, and then e to the power lt. That is less or equal, or maybe less or equal than e to the power l capital T, and then you have norm g1 minus g2, the constant c, and then taking supremum from the left hand side of over t from 0 to t, you will see that the norm is less or equal than that. Therefore, it implies that the norm of z1 minus z2 in the space of continuous functions is less or equal than ELT, the norm g1 minus g2c. That implies that that capital phi is Lipschitz continuous. Even better than we need is Lipschitz continuous. Um, Okay, and now we can use the contraction principle and Schilder theorem. Now, since z epsilon is equal to capital phi of wx epsilon, oops, we don't have w epsilon, we have square root epsilon w, we can use the contraction principle. Because square root epsilon w satisfies the large deviation principle in the space of continuous functions started from 0 with the with rate function. Maybe it's better to say with good rate function, we know that. Rate function I of f that is the 1 over 2 integral from 0 to capital T f dot square of t dt if f belongs to h 0 to 0 t and plus infinity otherwise. Maybe let me see. Let's check. Aha, here already I is reserved for the rate function of z. Maybe it's better to put here w, and it will mean that the rate function for w. And thus that epsilon satisfies the large deviation principle in C0t 0 with good rate function. Now we will write I as before. I of f is equal to, you need to take infimum of the rate function of w, of your old rate function, for instance computed in the point g, such that capital F of g is equal to f. The infimum is taken over all g, satisfying that property, or we can continue that it is the same as you take the infimum over all I w g, such that what does this equality means is that equality means that that function f satisfies the differential equation with the function g. Therefore, you have that f of t, such that f of t is equal to integral from 0 to t a f of s ds plus g of t. And also let's note that due to the uniqueness, of solutions, we have that the function f is bijective. Indeed, because first of all we said that that for all f for all let's see, we constructed the function f as a solution to this equation. First of all, we said that for every g we have a solution which looks like that, and also we know that this map is injective map. And let me see whether we need more. No, probably we need here. Oh, let's not talk about bijective because we say nothing whether f is surjective or not. Let's say that f is injective. It is enough here. Is injective. What does it mean? Actually, it means that this equality is obtained for, I mean, if f is fixed, then there is only one function g um, for which you have that equality. So therefore, actually, this infimum it is only the function, the value of I in that point. now I want to propose you some exercise that you will consider as an we will consider that as an homework exercise, because you see now what I want to obtain. I want to obtain the precise form of this function using, I mean, or I want to precisely compute what this is. So then I will need the following exercise. Is exercise. Size. In the script, it is in the lecture notes, it is 88. Let phi from C0, different color. Let phi from C0, 0t to C0, 0t be as above. Then, okay, here even we know more, then show that phi is bijective. The second, prove that G belongs to H0203 if and only if F is equal to, if the image belongs to H020T, and that follows from the fact that coefficients A is bounded. And three, we have that the dot, I mean, recall that that this equality here, it means that f of t plus integral from 0 to t a of f of s ds. No, I'm sorry, it is z is equal to that integral plus g of t. But now, when formally you compute the derivative, you will see the derivative here. That integral will kill that derivative, and then you have the derivative of function g. So therefore, the third exercise is that shows that, shows that g dot is equal to f dot minus a of f almost everywhere, for every g that belongs to H020T, and f that is the solution to the corresponding equation. Oh, you see that if G belongs to Z, then this dot exists, and turns out that by this exercise, dot for F also exists, and you have that equality. So therefore, now having this property, what you will see here, you see that, okay, when we take the function F, which is from this space, that also means that the function G is from this space, and then you know that this I is given by that equality. So let me continue that, but I will copy that part. Copy. And then continue. It is equal to, and then you have I of IW of J if f belongs, it is equal to f of j, and this f belongs to h 020t. Because once it is and if f does not belong, so then you have that this also will not belong. So then G is not will not belong. So you have, okay, let me compute also continue that. Does not belong. Here at the moment I did nothing, correct? I just split on two cases, but the first case tells me that, okay, if f belongs, then g belongs, and this can be computed as the integral, so therefore it is equal to the 1 over 2, the integral from 0 to t of the function g. But what the function g is, you have that equality, g satisfies that equality, so therefore you have that this g, it is f minus that integral. But by the previous exercise, g dot, it is f dot minus a of f. For here, you will have you will have f dot of t minus a of f of t dt if f belongs to h0 to 0t. And if f does not belongs to h2, then is not absolutely continuous with square integrable derivative, then also g does not belong. And therefore this rate function, it is equal to, here it is equal to plus infinity. It is equal to plus infinity if so otherwise. That finishes the proof of the theorem. Okay, we discussed here the first application of the contraction principle, and as I already said, next time we will talk about the large deviation principle for empirical distributions, and we will consider like simple case. And you will see that in simple case, the large deviation principle there also can be obtained via the Sanov theorem. We will need to make, first of all, some preparation and so on. We will do that everything. And after that, we will just formulate without proof the general, the general or the large deviation principle for empirical distributions in general case. And that statement is calls calls the Sanov theorem. It is everything for today. We don't have nothing to discuss more. I don't want to start a new topic because though it is also quite big topic, we will need to make a lot of preparation and so on. I would like to do that during one lecture. So therefore, today we will finish a little bit earlier. Thank you so much for your attention.